This work presents a framework to allow bipedal robots to work on constrained footholds by controlling the discrete transition of angular momentum. The problem is difficult due to its non-periodic nature and the need to precisely place the feet in a dynamic fashion. To tackle it, we separate the robot dynamics into output and underactuated dynamics. With sufficient control capability of the robot's actuators, reasonable output can be tracked by a low-level controller. The idea is then to focus on the resulting underactuated dynamics and stabilize it using controllable outputs. We use the linear inverted pendulum model to approximate the continuous underactuated dynamics of the robot. Using the closed-form solution of lip dynamics, the criterion for a lip model being able to take a step can be fully described by post-impact states lying in the blue region on the face portrait. This is characterized by the three viable conditions, where E stands for orbital energy. Similar condition transfer to robot dynamics with a tightened bound on orbital energy. The impact equation for underactuated dynamics can be written in closed form, so viable conditions can be realized by controlling pre-impact states. However, these quantities are determined by stone configurations. These quantities are underactuated states. This left us with only the COM vertical velocity to regulate post-impact angular momentum. To remain viable, the underactuated COM forward position is regulated by step duration, computed from lip time to impact function for pre-impact COM x reaching some ratio epsilon of the current step length. The last two conditions can be achieved by controlling the vertical COM so that the post-impact angular momentum corresponds to a desired orbital energy E star. Together with other polynomial-based trajectories, all the outputs are then tracked using a task space QP controller. The methodology is implemented in simulation with Ember and Cassie model. Here are some results with periodic stone configurations on Ember in MATLAB simulation. All of them converge to periodic working. Then is the random stepping stones and the resulting face portrait. We can see the evolution of face curve in continuous time is very similar to that of the underactuated limb model. As shown in the video, the user-determined parameter epsilon affects how lean forward the robot is at pre-impact, and E star is positively related to the robot's COM forward speed. Here are the results for stairs and flat ground stepping stones on 3D Cassie and high-fidelity gazebo simulation with ODE physics engine. Our method is applied on the sagittal plane, and H-lip stepping is used to stabilize the coronal plane. Working on randomly generated stepping stones is also demonstrated. In all scenarios, the orbital energy is stabilized close to desired, which is the black curve corresponding to E star and tilde Z star. The actual COM vertical distance to the slope is also stabilized near desired.